hopefully you will all be engineers. And what we want to know is, what do these things look like in real life? So here's a picture of a roller that I found. But to be honest, I've never really seen these in real life except on really old bridges. This is really what rollers look like. You take neoprene and you stack it, and neoprene is incompressible, so you can't compress it, but you can shear it. What this means, if you stack up neoprene like this, when you push this way, it really doesn't change volume much, but if you get a stack of neoprene like this, and you push it sideways, it will deform into a parallelogram and not offer much resistance. So that's what a roller does. So a roller, it provides a reaction vertically, but it does not have a reaction horizontally. Now there is some force horizontally, but it's very, very little, and we consider these stacks of neoprene as rollers in real life. Now, the reason I happen to know about this, it's just serendipity. I happen to have a research project on rollers like this. Well, what happened, this was in Louisiana, and it get really hot, and at night it would cool, and these bridges, which are really long, they would move back and forth. And we could never catch them doing it, but these rollers, or these neoprene pads, they would inch out slowly, and then every once in a while they would just completely fall out, and you'd be driving over the bridge, and then there'd be a gap like this. Fortunately, the rollers, or the pads that were coming out, the ones we were looking at, were only maybe a half-inch thick. Maybe that was a problem. They needed to be thicker to not slide out. And so you'd be driving, and then you'd hit a big bump, and you go down there, and sure enough, you'd find this neoprene pad on the ground. It had just worked its way out, ratcheted, and it would just fall out and go plop right on the ground, and we would find this thing on the ground. Okay, what about pins? What about these things? What do they look like in real life? So again, here's a picture of a really old structure, and look at that. That looks just like these pins that we were drawing. But nobody does that anymore. That's just, you can imagine how hard it is to put something like that together if you're building a real bridge. In real life, these are pins. You either bolt the end of one beam into the other like that, or you weld this fin plate. So this brown plate here is welded here to the column, and then you just put in bolts here. That's considered a pin. No moment. Obviously, there is moment there. There's a reaction of a moment, but it's so small compared to the strength of the beam, we call it a pin. So here's a swank structure at the University of Hawaii where I was doing my sabbatical. This thing has all the different types of connections in steel structures. Well, we also happen to have maybe this exact structure, because the plans are everywhere. We have this structure between the engineering building and the ag building. You'll see it by where you park your bicycles. And so here you see 3 examples of real life pinned connections. These are considered pinned connections. It's hard to imagine again, but that's this. Okay? And here are pictures of real life fixed connections. To make a fixed connection, basically if you have an I-beam like this, if you connect only to the web, this part, the vertical part, if you only connect there, we consider that a pin. And if you connect on the top and bottom, this is called the flange. If you connect the flanges, that'll be fixed. Okay, so here you see there that's connected. Okay, anywhere you connect on the top like that, or weld it across there, that'll be a fixed connection. And here in this picture, you see examples of fixed connections in these photos. A quick note about the weight of these beams. Everything weighs something, and the weight is at the center of gravity, or what we call the CG, and calculating that is quite a bobsy die. It's a lot of fuss, it's a lot of trouble. So for now, we're just going to give you the location of the center of gravity, but we'll learn how to do that later. And sometimes the weight of something like a beam is so small compared to the other loads on it that we won't worry about it. So for example, if we had a beam, and let's say the beam weighed 500 pounds, and you put 10,000 pounds on it, you could ignore that 500 pounds. Well, maybe not. But when the loads, let's say it was, I don't know, 100,000 pounds, and then it weighed 500, then yeah, we could ignore the weight of the beam. Okay, so here is an important part of this lecture. Well, the free body diagram is super important, but here's the procedure you'll use for all these 2D rigid body problems. So step number 1 is to draw the free body diagram. You have to do this. In fact, in chapter 5, when we do our homework, instead of having you hand in neat homework, when we get to chapter 5, I will have you hand in your free body diagrams, and those will be graded. If you can't draw the free body diagram right, you can't get the problems right. Okay, you draw your free body diagram, and the first thing you do is check if all the forces are concurrent, because if they're concurrent, then it's a particle problem from chapter 3, and that would really be a trick problem. I wouldn't do that on an exam, but on a homework, you might get that. Okay, once you've confirmed that your forces are not concurrent or meeting at one point, check if you have 3 unknowns. You should always have 3 unknowns because you will always have these 3 equations. Sum fx equals 0, sum fy equals 0. You've done those for particle equilibrium. You now have a third equation, some moments about some point p. You just pick any point, and if you're clever, picking the right point, you can make this last equation very handy. But anyway, you get a third equation. So you have 3 equations to solve for 3 unknowns. This is how it always works. Free body diagram, 3 equations, solve for 3 unknowns. Boss, that's Arabic for however. There is more than one way to skin a cat. That's an American idiom, meaning there's more than one way to solve this problem. You need 3 equations to solve for 3 unknowns, but if you want, you can get one force equation, sum fx equals 0, for example, and then take moments about 2 different spots, sum ma, sum mb equal to 0. That'll give you 3 equations to solve for 3 unknowns. Or if you want to be really different or unique, take moments at 3 different spots. I know this is a lot to absorb, but it'll become clearer when I demonstrate these principles in examples that we'll do in a little bit. But for now, make sure you understand how to draw a free body diagram and that you will get 3 equations with 3 unknowns. And one last detail is when you draw a free body diagram, you'll have supports, so you need to know what kind of forces are on those supports. But we'll continue this with more examples.